right, guys, what equation are you using here? Yeah, for part A. Well, what is the BCE? Sorry, what is the BCE? You probably want your half reaction sheet with the reduction potentials on it, as it has some, it gives you some help on what the reactions might even look like before you can finish with the balancing. I might just do a couple with you, and then the rest will be for you guys for homework, because I don't want to spend forever on this if we're not quite done with electrolytic either. Fine, tell me your 2 half reactions. Let's build it, okay? Fe2 plus, Fe3 plus 1 electron. So that was iron being oxidized. And what's the other one? Okay, so tell me are you just looking at the half reaction sheet and flipping the equation? Okay, so if you're seeing that the oxygen is being reduced to water, you actually, if you get the sheet in front of you, you can balance it, or you can look at the sheet and look for the one with oxygen going to water. You guys can find it on your sheet, or you can balance it. So you took oxygen and you made water, and then how did you balance it? So you needed 2 oxygens there. So there's 4 H pluses and good, and then 4 electrons because of the charge difference there. And then what? Right, so you can multiply this by 4. Total BCE is 4H plus oxygen plus 4Fe2 plus yields 4Fe3 plus 2 waters. And so we're going to deal with some of these more extended BCEs with electrolytic more specifically. Okay, so then really that's important because later on we're going to have to probably set up a queue with products or reactants. So we're going to need that, but right now we only need really what values for here. We need our E cell value or our cell potential values. So what is the E value for each of these? Standard conditions. Look on your sheet, guys. So 1 volts for the iron, and as it's written on the paper, no flipping of sign, is 1.23. So this is E, which is the reduced one? The oxygen one. So this is E red. This is the reduced one. This is the one that's oxidized. So you'll do E red minus E ox. So E cell standard is 1.23 volts minus 0.771 volts. And you should be able to do some of this math in your head, specifically the subtraction, because on the multiple choice you may not have the option for a calculator. So work that out for without a calculator. What is it? 0.46. So E cell is 0.46 volts. Okay, before you plug in information for part B, actually we may not be able to do this part in our head. All right, so you see there are 4 values given to us. These 4 values are information about each piece of the puzzle that matters in equilibrium. What are the only things we exclude in equilibrium in terms of products or reactants? Solids, and we definitely have something called KP. So KP will include gases, right? So pure solids and pure liquids are the only things that are 100% out. Do we have any of those? Right, H2O is our only pure liquid. That's the only thing will be excluded. Everything else will be included in our Q value. And these concentrations are given. In Nernst equation, you can mix your units, meaning molarity, and these atmospheres, because like K doesn't have a unit. Remember K's unitless? It's very odd for us to do this, but we actually usually don't mix units in K, but for these types of problems, you can mix them because it's very rare to see them anyhow. And then that pH is for the cathode compartment. What is this really telling us?
It's in acid.
It's in acid, but we've already balanced it, so we're kind of done with that part. It's telling us the H plus concentration because we need that for this part right here when we plug in the Q. All right, so It's hard to Le Chatelier's kind of think about that one because there's so many values that have changed. So what are we going to set up? What equation? This time we're for real, like calculation equation. E cell, which is our new E cell we're looking for, non-standard, equals E naught cell, which is calculated already. Is it minus point? It's minus 0.0592. What? It's, you guys have your notes equation. Pull out your notes. Because you haven't looked at this enough to even have it memorized, it doesn't sound like. You have your equation memorized. I mean, I'm asking for the memorized version like this, just because I think it's simpler to memorize. So 0.0592 over N. N is representing moles of electrons transferred total, right? And what is N here? 4 moles of electrons. You can see it right here. Because you can see that we multiplied across there, and that's 4. And then what? Yeah, this one's times the log of Q. And let's go actually set up Q's expression right now. What is Q's expression? Back to products of reactants. Remember your or actually, can we set up the expression first and then plug? Give me the expression first, like these. So like this will be iron 3 plus. Hold on. Remember the coefficients become exponents? This is like November, people, I know. Okay, so iron 3 to the 4th power. Water is irrelevant. Over H plus to the 4th power. I'm going to put partial pressure of oxygen because that's how it's given to us here. And that's just to the 1st power, and then iron to the 4th power. A little complicated, right? So we have to make sure we include, I recommend writing it out just so you don't have to, like, don't skip steps here. It's going to end up poorly if you can't plug it in correctly. So then your values up here will get plugged directly in there. Your N is 4. And when you plug all that in, your value is, I need space, sorry. Your value is, by the way, this concentration, what is the concentration of H plus? You can tell me straight from the pH. Without a calculator, what is the concentration of H plus if pH is 3? 1 times 10 to the negative 3rd, right? All right, you should be able to do that in your head, no calculator. E cell, under these new conditions, is 0.426 volts. So it went down a little bit because why would it go down? Would it be shifted to the left or the right? In terms of Le Chat's. Say again? Left or right. So there was obviously a shift left because there was a decrease in the electromotive force, and that's probably because the concentration of these reactants were lower than the concentration of that product. That one product went up to 3 molar. What standard condition? 1 molar, so the concentration of the product went really high. And if this went high, it needed to be consumed, so it shifted left. And these concentrations over here got smaller, which is going to, again, cause it to shift left. So it makes sense why it's lower, correct? Yeah? Okay. Tell me, actually on this, yeah, this is a concentration cell. Let's do the concentration cell. Go ahead and write down what you need to here for your setup. Concentration cells are ones where the electrodes are the same identity, the concentrations are different, and the concentrations are what's causing the electrons to flow, which is causing the electromotive force. You took notes on this. This is number 4. Anybody know who the anode is right now? Which compartment is the anode? The 5 molar one or the 0.01 molar one? Is this a guess? All right. Do you look at your notes? we specifically, and it's actually the other one, process of elimination, because I'm countering Lewis, right? Yeah, so you remember why. Okay, so maybe come up with your own version of this, but cathode is the concentrated one. Anode needs to make more ions, and as you make more ions, that's going to get you up to the concentration of the cathode, or they're eventually going to equal out. And if they equal out in concentration, there's no driving force forcing the reaction to go. That's equilibrium. That's when the battery is dead. That's E cell equal to 0. So we need to get the anode ions up. And the only reason you know that is because what process is, I mean, we obviously have zinc and zinc 2+, right? What's the half reaction at the anode? So what's the half reaction at the anode? You know what process occurs at the anode, right? Oxidation or reduction. Oxidation, so make this thing oxidize. Right. And so the cathode has to be the Zn2 plus 2 electrons yield zinc. We know they're the same half reaction. There's one just flipped because of the process of oxidation reduction. So if you're trying to figure out which is the anode, which is a cathode, the goal is for you obviously can see the cathode's going to be reacting the zinc. The zinc concentration is going to go down in the cathode because it's being consumed, and the zinc concentration is going to go up in the anode. Well, the only way that's going to work is if the anode has less concentration to begin with, so it can build up, and the cathode is concentrated, so it can go down. Okay, so just remember the anode is the lesser concentrated one, so that's going to be the 0.01 molar one. Okay? Even if you have to memorize it or come up with your own kind of phrasing or mnemonic for it. What is the standard EMF for this cell?
0.
Why 0?
Because that's standard, it's 1 molar per each one. And then that's at equilibrium because it doesn't do anything.
But why is it? It's not that it's at equilibrium, really. For this cell, EOX minus E, or E red minus EOX, what values are you going to be looking at? Both are for zinc, and so zinc minus zinc is going to be 0, right? It's the same E cell at standard for both, so that's going to be 0.00 volts because they are the same identity of electrodes, so there is no electromotive force between them at standard conditions, but there are at non-standard conditions, meaning different concentrations. So for the concentrations given, here's how I do this. I know that I have zinc 2+, going to zinc. Guess what? Zinc 2+, right? So we have the same half reaction, but you need to figure out which zinc is which zinc. Okay, so which zinc is this one going to this one? Oops, I'm sorry. Zinc going to zinc 2+. Which half reaction is that? Say again? That's the anode, right? So I'm going to put anode and anode. And that one, we've already figured out what's the concentration of that zinc 2+. 0.0100 molar. Okay, so then zinc 2 going to zinc solid, that's the cathode, that's reduction. So I've just put cathode. So this concentration is what? 5 molar. It's easy to write it out, and that way you can actually figure out what's going to happen to the E cell. What's going to happen to E cell before you even calculate it? 1 molar and 1 molar concentrations, E cell is 0. These concentrations, is it going to go up or down? Say again? Which way is it going to shift? Does everybody see it's going to shift to the right? You increase the concentration of a reactant, it's going to shift to the right. You decrease the concentration of a product, again, it's going to shift right. So if we know it's going to shift right, E cell should what? Increase or decrease? Increase, right. So the EMF is going to increase. So maybe just a couple points of a volt or tenths of a volt, but it's still going to increase. So then what you would do here is then plug it into your Nernst equation. E cell equal to E naught cell. What is E naught cell for this one? 0 volts. Minus 0.0592. What is N for this one? 2, because there is a 2 electron difference between the zinc as in its half reaction. Times the log of, this is the point that matters, right? This is the zinc concentration of zinc concentration. Well, which is which, right? So concentration of zinc product is the anode one. And that's just to the first power, right? There's no coefficient to deal with. And this is the zinc that's going to the denominator, which is the reactant one. Also to the first power, there's no coefficient. So then plug it in, and you get 0.0799 volts. And it did go up, so we kind of verify our qualitative or quantitative. Now, those are the concentration cell ones. Those are different than the normal cells. Do they make sense, though, at this point, after me doing one more example? Yeah. You have more examples in your notes, too. Okay, you guys will do the last one. I think it's gonna ask you to calculate K. Okay, so you have to look back at your notes. The only issue I had with part A was helping you set up the equation. Since transition metals have variable charges, I have to tell you the charge. What's the BC for this one? So it may not be that iron 2 is the actual form of the reactant. It's just telling you what iron will form. So if iron replaces zinc 2. Maybe give me some reactants. Say again. So iron's going to go to what? Well, so if you're saying iron 2 goes to iron 3, what's happening to nickel? Nickel's going to solid, right? So nickel 2 plus is being replaced. And when you're replaced, you take your ion form and you're forming your solid form. What's both of those doing? Both of those are reducing. So we can't have two reductions, right? This is 2 to 0, 2 to, no, this one's oxidizing, but on the sheet, this one, iron 2 to 3, is more likely, because these are all galvanic so far, okay? Iron 2 to 3 is more likely to be reduced than nickel. So if it's more likely to be reduced than nickel, that's not our half reaction, because nickel is definitely being reduced because we're saying it replaces nickel. So it's not that one. It's actually going to be iron solid going to iron 2. That's oxidized, yeah. Iron solid going to iron 2, because it's just telling you iron 2 is involved. It's not saying necessarily that's the solid. I mean, that's the oxidation state of the solid, but the solid is a free element, so it has to be 0. So it's oxidizing to the 2 plus charge there. Okay, so that gives you some help on that. The other ones are not that. Okay, I'll go over those tomorrow. Okay, let's do some electrolytics. Okay, so knowing kind of what we talked about already, you're probably assuming electrolytic is 100% opposite of galvanic, right? So everything that's different would be what? E cell is positive for galvanic, E cell is negative for electrolytic. Delta G is positive, and we also have something that's going to force this reaction to occur. So galvanic cells happen by themselves, spontaneous, thermodynamically favorable, whatever you want to say. They don't require any outside intervention. So the electrolytic cells do require outside intervention. So there's an electrical energy being pushed to the galvanic cell, to the electrolytic cell, and then the electrolytic cell is able to do its redox, change electrons, make energy, whatever it is. Guess what the electrolytic what the electric energy is coming from, though, or where it's coming from? It's coming from a battery, and the battery is a galvanic cell. The galvanic cells run the electrolytic cells. What? Okay, so from direct current battery, DC battery. So this is kind of the background. I have some pictures for you, and then we're going to do some calculations. And we get out earlier today because of teal, so. I get out 8:35, so I got 45 minutes. So that's why I'm just going to keep talking, okay? So since the DC battery, which is the galvanic cell, is forcing the non-thermodynamically favorable, so electrolytic cells are non-thermodynamically favorable. Since the galvanic cell is forcing that to happen, we call that a coupled reaction. You may remember this a little bit from thermodynamics, where one reaction that's not thermodynamically favorable is paired with one that is thermodynamically favorable, and that's going to fuel the other one to kind of give it its activation energy, kind of get to start. So that's the key point here, is that they have to be coupled, galvanic and electrolytic, to make them occur. And batteries are galvanic cells. So they have to pump electrons to the cathode, so the galvanic cell will pump electrons to the cathode, and it's going to actually create charge buildup. And that charge buildup is neutralized by metal plating out. And plating out means that the metal, actually metal solid, makes a beard. Remember a beard on the galvanic cell? It makes a beard on the cathode of the electrolytic cell. And that's actually valuable to us because we can collect the metal, we can electroplate stuff with that, we can do all kinds of things with plating out metal. Most of our, or not most, a lot of our jewelry is electroplated. Chrome wheels on cars are electroplated. A lot of things kind of abuse this whole chemical process. And do not draw these cells right here. I have a different cell for you that gives us a bit more contrasting nature of the two cells. But you will see the flow of electrons become opposite, and that's because in a galvanic cell, which is this one's galvanic, the flow of electrons are coming from the anode to the voltmeter, and the voltmeter is reading it as a negative kind of deal because it's sending electrons towards it, and it's sending electrons to the cathode, so the voltmeter is reading the cathode as positive because it's pulling electrons towards it, and electrons, opposites attract. Well, since the battery, which is galvanic, again, is kind of the mediator here, what's happening is this is the anode of the electrolytic cell, which oxidation is always occurring at the anode. I don't care where we are, what we're dealing with. Oxidation occurs, doesn't matter if it's electrolytic or galvanic. The anode is going to send electrons someplace. Well, the only reason there's a pull for electrons to leave is because the cathode of the galvanic cell is attracting electrons, basically. So the electrons are traveling this way from the anode of the electrolytic to the cathode of the galvanic, and then inside they're doing their little switcheroo. And then the anode from the galvanic is, of course, is also oxidizing. So it's sending electrons out of itself to the cathode of the electrolytic. And of course, there must be some sort of exchange of charge, and they don't necessarily have to have a salt bridge. They can have a porous barrier, which is why a lot of times they're depicted differently, so you can contrast them better. But the salt bridge, again, is just going to allow for the charge buildup to be eliminated, or for something else to kind of intervene so that the flow of electrons will continue. So they look a little different. So regardless of type, anode oxidation, cathode reduction, and then these are some applications of it. Write down a couple of applications for yourself. Specifically electroplating and isolating pure substances. This is how we get like pure metals out of ores, out of mines, from rocks and stuff. So a lot of times that's called electro-refining because you're refining an impure substance into a pure substance. I just don't want you to get caught up on the words. If you see those words, they're meaning electrolytic cells. And then you don't have to write down this, but this is what we're basically going to learn today: how to relate reactants to massive products made, or charge made, or time it takes to electroplate something. So we're relating our reactants to a lot of different variables that deal with charge and time. Or like actually volts made, amounts of electricity. So we got chrome-plated wheels, and then we've got like markings on jewelry. How do you know if something is electroplated? Chrome wheels here. Whenever you look on like some packaging, you'll see gold-plated silver. That just means they put the ring or jewelry inside of a little cell, and they set up the galvanic with the electrolytic, and they just plated the gold. It's much cheaper to do that because it plates it like a nanoscale versus like dipping it in gold or something. So they're just cheap and they don't want to do it. But they're using science to do it. Okay, so I'm going to move forward. You guys can finish up if you need to later. This is kind of, you can see this is kind of how the cells are drawn. There is no division between the chambers. You will usually see some sort of porous barrier between them. But more importantly, you should see a voltage source, most of the time labeled DC, attached to another chamber, which is the electrolytic chamber. So we kind of already talked about a couple reactions. You guys okay on a couple of reactions? Definition. Write down if you need to. Let's look at this. Let me look at my sketch. Okay, here's my sketch. Sketch this for yourself. Look how pretty it is. And then we'll talk about the two types of electrolytic processes we are mainly concerned about. So we usually have one chamber. We still have 2 electrodes. Most of the time, the electrodes are submerged in some sort of liquid. And that liquid is either, I'm going to scroll back up for you in just a second, that liquid is either molten salt, like an ionic salt, molten. What does molten mean? Not lava hot. It does not necessarily mean lava hot. So most of the time, ionic salts are what at room temperature? Solids. Molten just means they've turned liquid, okay? So it just means liquid, but it's pure liquid. It's not aqueous. It's pure liquid salt. Okay? Not aqueous. Secondly, you can also have this submerged in water, aka aqueous solution. And the only way you're going to read in the problem and know it's water or an aqueous solution, it'll say a solution of copper 2 sulfate or a solution of silver nitrate. So that solution part is telling you it's in water. And that's important to be able to figure out from a problem. Okay, so the porous barrier is like the salt bridge. It allows for ions to flow so that there is no charge buildup as best as we can. But let's say this is the anode and this is the cathode. In this case, this is the anode. You know it's going to be what? Oxidizing. And where is this electrons going? Right, they're going to the DC cell. The DC cell's cathode must be on this side because the electrons are leaving here, going to the positive cathode of the DC cell. And you will sometimes have to label charges. It depends on how detailed they want, but the electrons are flowing here to the cathode. That means this side is the anode of the DC cell, meaning this side is the positive cathode. Well, duh, we got cathode right here, but we know the electrons are flowing to the cathode here. Well, if the electrons are flowing here, they have to be captured by something. And generally, let's say this is a copper 2 sulfate solution. If this is copper 2 sulfate, we got some copper 2 and we got some sulfate hanging around. Okay, sulfate's actually a spectator here. What's going to happen at the cathode? Electrons are coming in. So it's going to make solid, make a beard, and the 2 electrons have been captured. Yes? Okay, so there's going to be plating here. That's what I mean by plating, electroplating at the cathode. If you memorize nothing else from today, electroplating at the cathode. That is a definite need to know. It's a multiple choice, easy question to get right or wrong. Okay, so knowing that this is copper 2, what color was the solution? Blue. Maybe over an hour of this happening, copper's plating. What color is the solution now? Not as blue. It might even be clear. All the copper could have precipitated out, so it would no longer be blue, it would be clear. That's a question they usually like to ask too. What observations could you make about the solution? The color change of the solution is due to the copper being pulled out from ion form to solid form. Okay, this part's on your notes. Write down, fill in the boxes. If you pull out your packet, I'll tell you where it is, and you guys can write down. Anybody with the packet nearby? On page 6 of your packet, I have a little table set up for you. So like I said, either we are dealing with ionic salts undergoing electrolysis of some sort, or aqueous solutions undergoing electrolysis. So the first boxes have you set up with, if I have a salt, I obviously have a cation and an anion. The cation is the one that's going to be at the cathode because it has to gain electrons. That's the only thing a cation can do, really, is gain electrons. So if the metal, and usually cations are metals, if they gain an electron, they form their metal solid. Well, what's so interesting about metal sodium solid? Explodes when? With water. Do you see water in my battery at all? No. That's because I can't have water present with molten salts because most of the molten salts are going to make some reactive species that's incredibly reactive that would explode. That would just not be ideal for us trying to put together with the battery. I don't have all these notes on your on your table. So you need to fill out the table. You have to memorize this. There's no, I mean, you might be able to figure out from the problem, like, what's the only option for one thing to do and the other thing to do, maybe oxidize and reduce, but memorize and make sense of it. So the anode that's present in the salt has only one choice. It must get rid of electrons, and that is loss of electrons, oil. So the nonmetal getting rid of electrons will form its free element. Well, sometimes, a lot of times, our ionic substances have halogens or halide ions, and those halide ions, when they oxidize, they form halogen gases. So you might even see bubbles forming at the anode, and you'll see that in your lab tomorrow. You should be able to make observations at the anode and cathode to help support your predictions or support your answers. So this cannot be in water because reactive. Okay, a lot of our alkali and alkaline earth metals are very reactive. But that's it for the molten ones. Like, there's only 2 ions, guess what? They're both involved. And you can figure out really easily which is oxidized and reduced. Is that one okay? Is there really a question like who's going to be oxidized and reduced here? Yeah, cations and anions, cations at the cathode, anions at the anode. They rhyme, right? So make sure you know that. All right. So our second, let me show you the battery first. So this is the one that's really more interested in isolating things from ores, because those pure metals, which are so active, you can't really get them out through aqueous solution. So a lot of times this process is used for ores. So this is the battery is actually all together. You can see the beaker here. So the beaker with the sodium, chloride, molten salt, and the orange color here. And then these are actually the electrodes. The electrodes are these metal things, and they even indicate the gaseous chlorine coming off. No, on a battery, not sure if you have to memorize this or not for the AP exam, so write it down anyway. This is how a battery is denoted in physics. Okay, give yourself a quick sketch. The bigger, the longer line is the cathode, and usually there's a gap, and the shorter line is the anode. Sometimes there'll be 2, like a long, short, but regardless, you should know the long side is the cathode, the short side is the anode. They've started using this more in AP Chem, so just making sure you're aware. And I have it on some of my answer keys too, so you're aware. So what is the BCE for this reaction? Where are my 2 half reactions? Real quick. Half reaction at the cathode, what is it? Knowing this is molten sodium chloride. Na plus electron yields. Na solid and Cl2. So where are the 2 electrons? Here? Okay, but what do I need? Right, so then the half reactions, these would be the cathode and anode reactions, and then you would balance them out by making your electrons equal and then cancel. So then what would the total reaction be? So you multiply here, good, and then goes to, this is a plus, did I write the plus sign? Sorry, that's a sodium cation, yields what again? Chlorine gas and 2 Na solids. That's the full reaction. Okay, so if we have something in water, this is a little bit more complicated because you have lots of variables. You have the salt with cation and anion, and you got water. And water is actually able to be oxidized and reduced. So you have 4 options here. And you must prioritize them in this order. Okay? Prioritize them in this order. If you have an anion that is very, 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 very likely to lose electrons, meaning usually a halogen, a halide ion is going to be it will be oxidized. Okay? So these right here, because you can force electrons. I know a lot of times, like this obviously has octet right now. It really doesn't want to lose electrons, but before it did have 1 less electron, so we know that it's possible. So a lot of times these are going to be reactive halides, and you could put the 2 there for like 2 chlorines, for example, chlorides, yielding chlorine gas and 2 electrons. That would be what we're doing. So if you have any other anion, like for example sulfate, so no sulfate, nitrate, phosphate, any of those, they're not going to be the one that you prioritize to be the anode. So only if you have a halogen will you choose that to be the anode half reaction. If you don't have any halide, you must choose water to be the one that's oxidized. And water oxidized looks like this. Where have you seen this before? We just write this down, right? We wrote down the opposite of this with oxygen. Remember we had oxygen being reduced and we flew it the other way with producing water? That reaction's on your sheet. Like it's actually on the standard list that's actually from positive to negative. It has a box around it. Okay? So a lot of times they'll give you that one, but if you are forced to do it yourself, can you make that half reaction by yourself? Water, single water forms single oxygen. Balance it by adding a 2 here, balancing it by 4 H's there and 4 electrons there. You can do that half reaction. You can do it. If you can't do it, then let me know later. Okay, so that's how you choose the anode. How do you choose the cathode? The cathode, if it says in acid, it might say in concentrated weak acid, or it'll say in strong acid. The concentration of the strong acid really doesn't matter, because strong acids, they 100% dissociate. So strong acids make 100% H pluses, so they're going to create a highly acidic solution. Weak acids, they don't make 100% ionization happen, so they're going to make little bits of H pluses at a time. So they must be concentrated in order to produce a significant amount of H pluses, which would give the solution overall a highly acidic solution. So if acids are present generally, you're going to end up making hydrogen gas at the anode. At the cathode. Okay? And you would see that as bubbles. So that would be an observation you make. If your solution is non-acidic and you have a salt and water still, not an acid, the only way your salt would be involved here is if your cation was a transition metal that is highly reducible. How would you figure out something is highly reducible? What could you maybe consider? A reactivity series, right? You think about your transition metals, who are the most active ones, who are the least active ones. You can also look on your list if you have it to see who is more positive in terms of its E cell. Positive means you're more likely to be reduced. A lot of times those are going to be things like copper, silver, gold. Who's lower on the activity series? Like group 1. Group 1 is row 1 of transition metals, chromium, manganese, iron. Those are all kind of more active. The reactivity series goes group 1, group 2, group 3, except for surprisingly low copper. And then you can see like molybdenum, silver, cadmium, I don't think what else, common platinum. You actually can plate out. Where's chromium? Maybe chromium. So those are really common transition metals that we plate out. Okay, and that's because if you have an alkali metal in your salt, alkali metals are very reactive with water. They would explode if they were undergoing here, so we do not use alkali metals here. So if you don't have an acidic solution and you don't have a transition metal, you have to say, water is the part that's going to be reduced. So sometimes you have reactions where water is the anode and water is the cathode. Okay, these reactions are not simply opposite. What do you see that's present here that's not present in the first one? Say again? Hydroxide. So what does that mean this solution is in? Base, not acid. Because if it was an acid, guess what, guys? We never would have made it this far. We would have used the first one, right? So this is when it's not in acid. This is when it's in base. If it's not in base, just note that it's not in acid. If it's in acid, you have to use the first half reaction. If it's not in anything else, it's probably in base or it's just pure water. Okay, so is that balanced? Yeah, okay. So let's go. Let me show you two things first. Do you guys remember going over this? I'm trying to think about, I'm going to do some problems here. Do you remember going over the purple stuff up there? Current flow. Creation of volts just because electrons are flowing. That's all electricity is. We went over that there like the first day, just talking about electricity. But now we're actually going to start to quantify the electricity in terms of its charge. Charge is represented by what letter? C is coulombs. Coulombs is the unit of charge. Q. Q. And I'm trying to draw that Q different than the heat Q. Q is current. Okay, Q is current. And current, or not, sorry, Q is not current. Q is charge. I is current. I'll show you, let me show you this here. Okay, there are multiple variables coming into play here, okay? So you remember seeing this on your notes. Q is charge. N is moles of electrons. What is F? Faraday's constant, which is 96,485 coulombs per mole of electron. So how does Q come out to be? Coulombs. You multiply moles of electrons times coulombs over moles of electrons. Moles of electrons cancel, yes? And you get charge, okay? So Q is charge, meaning coulombs. It's represented as coulombs. But a lot of times we don't denote it as Q because a lot of times we don't simply want to just calculate charge. So that's not something you're going to see with me a lot, but it's on your reference sheet. Okay? So they have on your reference sheet I is Q over T, I think. I think that's how they have it on your reference sheet. Does anyone have their reference sheet available? I think it does. Thanks, Matt. Down the very bottom. Funny. I is Q over T. Now, that's just something that's going to help you see what I represents. If I is current, current is coulombs over, guess what time it is, guys? Seconds. Coulombs over seconds, that unit, that derived unit is amps. You've heard of amps before. So many amps are going through the wire. Amps are just a unit that represents current. Current is a thing. Amps are its unit. Okay? That's why I kept saying not current, because charge itself is not current. Charge is a unit of, charge is represented by coulombs. Current is represented by coulombs over seconds, being the amount of charge that passes per time. And we represent that by amps. So I need you to organize your thoughts here. Write down what you need to. Because there are some things we're going to use with this, solving problems in just a second, as you can see here. So there are some constants to know. There's some conversions to know. There's some units, derived units to know. So current is amps. That's coulombs per second. Faraday's constant, I usually round to 96,500 because I'll try to do the math in my head if I can. Specifically in multiple choice. Coulombs per second is Faraday's constant. That means 1 Faraday is equivalent to 96,500 coulombs per 1 second. So you could always flip that equation around as needed. And we use the BCE to figure out moles of electrons to get in, or moles of electrons related to moles of metal plated out or something like that. So we'll look at that for mole ratio purposes. So I'm going to show you some examples first, and then I think you'll kind of get the hang of it, okay? So these are calculations based off the process of electrolysis. Give me a thumbs up when you're ready. And maybe smile. I don't have any water and I'm coughing here. I'm just trying to stay with you guys. And there's reading in your NSMI thing on some of this background too. I feel like if you're comfortable with the units and what relates to what, you'll be fine. Okay. So, are these questions on your notes? I think there's she's 7 questions.
Yes.
Yes. Please put a star on those questions. That's exactly what we're doing right now. Put a star on those questions. We're doing them right now. I just want you to know where they are so you can write down the givens with me, and then we're going to keep going. Okay, guys. So number 1, I want you to break this down like you did in the very beginning of honors chem. What are the questions? What are the conversion factors? What are the givens? Okay. So what mass of copper? That's our first question, right? So what are we looking for? What unit? Grams. So the question, grams copper. Okay, I'm showing you how to solve a problem. You need to be solving these problems with me. What's happening is you guys are not solving problems with me and you don't know what to study. So solve these problems with me. I'm requiring it. I should see everybody writing. Okay, so what's the mass of copper? Plate it out so we can see we're talking about electrolytic cell. When 10 amps is applied. What is 10 amps equivalent to? 10 coulombs per second. You can see that's a conversion factor because it's fractional. A copper 2 sulfate solution. So what is this telling you? Should be indicating to you stuff about the cell. It should be indicating to use the cathode and anode. Who is the cathode? Let's go in order. You guys had anode at the top of your cell, right? Okay, just jump right in. Anode, who's the anode, guys? Okay, hold on. When you see copper 2 sulfate solution, you've got copper 2, you've got sulfate, and you've got water. We're in water. Look at your water table. Anode has to be water because there's no what? There is no halide, right? Do you see in your table? That's our priority. There is no halide. Water must be the one oxidized. And this question, this specific question, I may not need it, but in the FRQ that's extended, it'll have you draw the cell, it'll have you do a bunch. Okay, so I'm trying to get you comfortable with identifying. Water is the anode. Okay, so if water is the anode, look at your list, your table for now. Your priorities of the cathode is what, and what? Acidic solution. Does it say that? No. Okay, next. Okay, do I have that?
Yes.
Yes, I have a transit. Remember, it's transition metal. I have copper. Copper 2 plus is the cathode, guys. Okay, we're not even going to go down to the third option of water. Do you see how that table is useful now? Okay. So if that's just for general information that we need to know. But tell me real fast, what is the half reaction at the cathode? Copper 2 plus. You know it's being reduced, right? So you're adding electrons and it's going to copper solid. That is the interest. That is the half reaction of interest. We are going to need this later, so do write down that half reaction. We could write down the entire reaction if we need total moles of electrons. We don't need that actually for this question. I know I need the half reaction. Okay. All that was just to figure out what the half reaction was. All right, for 30 minutes. All right. I want you to think of this one. That's our question. This right here is a conversion factor. This is also a conversion factor. You can relate this. You can say 2 moles of electrons per 1 mole of copper plated out. Do you see that as a conversion factor now? So what is the starting point? The only thing that's not a conversion factor, right? 30 minutes. You cannot start with a conversion factor. You have to start with 30 minutes. 30 minutes. All right. What's my next step then? Because seconds isn't included in conversion factor, no minutes here. So 60 seconds, 1 minute. Okay, use your rules of dimensional analysis. What has to be my next conversion? So the one with coulombs and seconds together, I have to get out of seconds. So this is going to be flipped. No, sorry, it's written as 10 coulombs per 1 second. Okay, now I'm in coulombs. But my question is mass. What's the only other conversion that has coulombs in it? Faraday's constant. Good. Faraday's constant is 96,500 or 485 coulombs per second. Sorry, that is per moles of electrons. I do that all the time, guys. Sorry, that's per moles of electrons. So I'm going to take that and flip it, right? So the coulombs are going to go on bottom. 96,485 coulombs per 1 mole of electrons. Okay, I'm very close to mass, right? I'm in moles of electrons. What do you think my next step is?
Use that half reaction to get to solid copper.
Yes, I'm going to use the relationship between moles of electrons transferred to moles of copper solid. Moles of copper solid, I can then go to grams very easily. So 2 moles, this is where you have to employ the coefficient here. 2 moles of electrons are transferred for every 1 mole of copper plated out. And then your last step would be what? Molar mass, which we have not used in a while, right? So 1 mole of copper is 63.55 grams of copper. Cancel, 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 calculate, calculate, calculate. I'm going to leave that and let you kind of digest that for a second. Because it's dimensional analysis to the extreme, right?
That's a lot.
But if you know the relationships and you know the units, you cannot get this wrong if you know how to do dimensional analysis, which we've known since like, I don't know, a year and a half now, I feel like. Okay? So, in this one, our grams of copper plated out 5.93 grams. Good. How many sig figs? And remember, you exclude any metric prefixes because they are simply for conversion, not as a measurement. 5.93 grams of copper. I think we need 3 sig figs because of this and the coulombs. This is kind of a conversion factor, not a measurement. This is not a true measurement for our problem. That's why we're not complete. Okay, who wants to do another one? Thank you, everybody. Thank you. Okay, so number 2. Did that make like 1 to scale 1 to 10? How do we feel about that one? 10 meaning you're awesome. Okay. Above 5? Above 5. Okay, even if we're above 5, that's good. Okay. So now our question is not regarding grams. Our question is regarding what? Number 2. Time. So time. The question is time. Must a current of 5 amps, and tell me what amps are in terms of their units, their true units. 5 coulombs per second. It's nice to write that down because that way you don't forget the units there. Must be applied to a solution. Okay, what is that screaming to us? Water is present. Think about that as you're thinking of your half reactions. Of silver nitrate, okay, to produce 10.5 grams of silver metal. Okay. Let's think about the cathode anode part just because I want you to practice that, okay? That's one of the hardest things to do. Cathode and anode. Anode was first on your table. Who's the priority for anode? Well, who's priority, like in general, who's priority? Halide. Do we have a halide? No, you must go with water. Water is the anode. Okay, you know water is going to be producing what in this case then? What's the half reaction with water? This is the anode, this makes oxygen, right? So we will see bubbles in this cell, okay? What's the cathode then? Because what's not present?
An acid.
An acid, right? If this was an acid, H plus would be present, we'd be forming H2 gas. But in this case, silver is not a reducible metal. Silver ion is being reduced to silver solid. We need this because we need what? We need the mole ratio for the conversion factor. We need this is a 1-to-1. Okay, so that's the anode. Great. So what is our starting point, guys?
About 10.5 grams of silver metal.
Right, so you're going to start with your grams of silver metal because everything else is a conversion factor or question. So starting off with your 10.5 of silver, where's your next step? Logically, your next step. Convert to moles. 1 mole of silver is 107 point. 87 grams. Okay. Next logical step. I'm in moles of silver.
Go to moles of electrons.
How do you know that?
Because that's how we get to amps and stuff.
That's how we eventually get to amps, and then we can eventually get to time. Because I'm stuck at moles of silver. This is the only thing that's going to get me out of moles of silver into something more usable. So 1 mole of silver transfers 1 mole of electrons via its half reaction. Okay, logical next step. Who has moles of electrons in their units? Faraday's constant. What goes on top?
9645.
You can go 96500 or 9645. I don't care, but you'll see our answers might be slightly skewed depending on which one you use. And that Faraday constant is per 1 mole of electrons. Okay, so moles of electron cancel. Now we're in coulombs, guys. So I'm going to take my coulombs per second and invert it. So 5 coulombs per 1 second. And I'm actually going to go ahead and convert to hours. How many seconds are an hour? 3,600. So 1 hour 3,600 seconds. Okay. Okay, got you guys. That's my calculator sound, like every calculator makes that sound. 0.52 hours. I went to hours because I just want to make sure you're good with going to every unit, okay? So it would take half an hour to get 10 grams of silver. I'm feeling good about this. That's only if my battery, my DC direct current battery, was supplying 5 amps. Okay. Okay. So you can imagine how could I decrease the time to get this much silver? What can I adjust? So increase the amps because it would be dividing by a larger value here, or what? Not really anything else. Never mind. That's it. That's it. Okay, let's see. Yeah, don't this one. No, I'm going number 4. You guys can do that. I give you specifically how much silver transfers. Put a star on that one. You guys can do that later. Going number 4. 10 liters. So write down your givens with me. I love these kinds of problems. I'm going. I'm like the Energizer Bunny. Okay, let's just do this. 10 liters. I have the direct current coming in. The battery. Okay. Saturated silver nitrate. What does saturated mean? Full of ions in water. Okay, you should understand saturated solution of silver nitrate. It does mean it's in water. Okay, so I'm gonna put water up there just to remind you. Electrolytes for 1 hour. Okay, so we got 1 hour given to us, 1 amp given to us. 1 amp is whatever what. 1 coulomb per second. What is the final pH? We haven't seen this yet, okay? What is that actually asking? So maybe the concentration of hydrogen ion or the concentration of hydroxide, and we could backtrack. Let's see which one it's really asking for before we move on. Thank you. So that's going to be us thinking about anode and cathode before we figure out which one we're actually directing ourselves to. Okay, let's go and do that. Anode. Why water? Because it's not a halide. Okay, we're on that section. I'm just trying to make sure you're starting to memorize, okay? Anode is the water going to what? Don't look at your sheet. Oxygen. Okay, we know we're going to oxygen. Let's balance this half reaction. Okay, but what do I need to do to balance? 2 waters, 4 H pluses, and 4 electrons. And how do you know this is oxidized? Simply by looking at the half reaction. Where are the electrons? They're on the product side. They are being lost to Neverland, okay? So they're lost here. That's how you should see oxidized. So thinking about your chart, you have, what's your priority? Acid. Do we have acid? No. What's next? So reasonable. I'm going to keep saying transition metal, so you're not just going any metal, okay? So do we have a transition metal? Silver. Silver ion must gain an electron to go silver solid. Balance. Multiply by 4. So you get 2 waters, 4 silver ions, yielding oxygen plus 4 H pluses plus 4 silvers. Okay. All that is to help us figure out who the heck we're looking for pH, which is obviously which one now. So the presence of H plus is going to help us figure out the pH at the end, so screw the hydroxide. And then this might help us later on with a BCE mole ratio. Okay? So tell me which one, how we're starting. Start with what? Before you jump to conclusions, let's start with 10 liters. Where am I going to go? Right, so you might write down 10 liters like, yeah, let's go, but there's no molarity to go from, right? You can't cancel liters. But think about in the end, this is asking for concentration, right? What is this going to help us get? Moles, which we need to divide by 10 liters to get the concentration. So just think ahead there. Okay, so now what I'm going to start with? 1 hour. Okay, process of elimination. 1 hour. Get me to a usable form. Let's go to seconds. What's that conversion again? 3,600 seconds per 1 hour. You should memorize that. Seconds, logical next step is amps, coulombs, right? So 1 coulomb per 1 second is what amps tells us. coulombs. Faraday's constant. You're all over that. Okay, so 96, 500, or 485. And since I have a calculator, I'm going to go with the real number, right? Per 1 mole of electrons. Okay, moles of electrons. But you're saying 4, and then you're going to compare that to what? You're right, 4 moles of electrons are transferred. So per what H plus? How many? 4 moles of H plus, right. So the relationship was, and you can see the relationship here, but I wanted you to balance it out so you could have practice that too. You should see there's a relationship of 4 to 4, 4 moles of electrons for every 4 moles of H plus. Still not all the way to a usable form to get to pH. So what do I need to do here? Right. So 4 moles of H plus are the only units left. Divide by 10 liters to get to molarity of hydronium or H plus. So hydronium is I'm calculating for you guys, okay? 0.00373 molar. How do I get to pH? Negative log, that's it. Okay, so negative log of 0.00373 gives me pH of 2.43. Yeah. You feeling like a beast right now? Yeah? All right, we have 10 minutes left. You guys are going to solve 5. Oh, no. 5 and 7.
We only have the first.
Okay. I'll put 7 up here too. You guys have 10 minutes. You guys can solve for both. 5, you start there. I'll put 7 up here now too. I really want to do 7 before we leave. Yeah, today. Before we leave for the year, yes. Totally are. Do you? Gosh darn it, I'm sorry, guys. I keep bouncing around here. There you go. Okay, we decide on homework while you're starting this, okay? Alright, I'm not going to assign you FRQs tonight, but we are going to in class tomorrow. We're going to get our lab done in like 40 minutes. So you can have 40 minutes for FRQs. I'll show you this report. You're still number 5 or number 7? 5. I'm optimistic, okay? Just let me be optimistic. Yeah. If it tells you platinum's charge, that is how you determine the moles of electrons lost or gained. I guess gained in this case. So if platinum 4, PT4, you know it's plating out because that's how electrolytic cells work. They're creating a solid metal that's usually being plated on something else. There has to be 4 moles of electrons change to get that far. So that's how you can figure out that part right there, that half reaction is useful. And then grams. Nick, what's your answer? 60.0. I'm expecting like once you figure out how to get started in the half reaction list of interest, it's just dimensional analysis. I mean, you do have to know, what coulombs and what Faraday's constant is, but other than that, this is like, I love this part because it's just units and math, right? Everybody's favorite, right? Alright, as you're looking at the next one, give me some thoughts. Positive thoughts, right?
Lots of gas stuff.
Gas stuff. So what did you say? PVX and RT, how do you know? All those things that go in PVX and RT. So what are you going to solve for in N?
Moles of
Why?
gas.
Why are we solving for moles of gas? Because that's the one thing you don't have, but why in the heck is that important in this question?
Because we gotta get to time.
That's not a direct conversion between moles and electrons and time. Okay, so from moles of the gas to moles of electrons
Faraday's
to Faraday's to amps.
Which gets time.
To get time. Okay, are you who's starting to see the light? Okay,
I see the light.
let's keep seeing the light then together. We'll finish this one together. How long time? Write this one down with me. This is a quality FRQ. Quality, because gases have to sneak in every now and then, and they're going to start now. Will produce. This is V. This is not quite temperature, but temperature kind of. We'll get it to Kelvin in a second. This needs to be in pressure in terms of atmospheres. And then we've got current down here at 2.13 coulombs per second. Okay, so PV equals in RT. And of oxygen is what we're solving for, so PV over RT. No. Okay, so usually I like to do this in one swoop. P is 738 millimeters of mercury over 760 millimeters of mercury. That's our P. V, 2.62 liters. Remember to include your units lazy people. Not that you're lazy, but you tend to sometimes on P's and RT. R, 0.0821 atmosphere liters per mole K. Kelvin, 26.2 plus 273. So so you can see that I'm just literally including every mini calculation in the bigger one. And then N, whoa. Let's figure which page one? Okay. N is 0.1037, or sorry, 57 moles of oxygen. I didn't round because I don't want rounding error. Okay, what am I multiplying this by? You don't have a half reaction, but you know one that's of interest. Anytime you've got oxygen being produced, and you can see platinum's at the anode, it doesn't say solution, my bad, it doesn't say solution, solution with water, okay? What is the half reaction with oxygen and water? You've written it down 3 times today now. So for every 1 oxygen, there are how many electrons transferred? 4. So it's 1 to 4 ratio. Okay, so keep that in mind. 1 mole of oxygen has 4 moles of electrons transferred. Next conversion. Because we need to get to coulombs, right?
Yes.
So 1 mole of electron has 96,485 coulombs in it.
Yeah.
Okay, and then,
Then we do
so coulombs are on bottom. What was it called? The amp 2.13. 2.13 coulombs per second. And we're going to hours because a lot of times this stuff takes a while. So I like to make bigger units so it's smaller numbers. And then that's 1 hour to 3,600 seconds. Okie dokie. That is 5.12, or sorry, 5.21. 215 hours. I don't know why I have 4 sig figs here. It should be 3 sig figs. 5.22 hours. Okay. Whew. So sorry, that was my grand finale. I want to make sure you incorporate gases into electrolytic. Okay, so I can update you guys on the homework on the website, but the electrolytic cells the nerves problems that we started this morning. There's 6, 7, 8. Those last questions regarding electrolytic cells. Do those, and then the lab procedure part. Basically, under the electrolytic lab, guys, look at the electrolytic lab right now, because I'll have you guys claim it. Same group says microvoltaics. Okay. Same group is microvoltaics. Let's claim a cell, and then that way you guys can actually know right now before you leave. I'll turn on announcements in a minute. Sorry, took us a minute to get started. So electrolytic cells. What page is it? Page 26. So these are the cells. Ready? Potassium iodide, potassium sulfate, hydrochloric acid, copper sulfate, silver nitrate, and nitric acid. 1, 2, 3, 4, 5, 6. 6 cells, okay? So I'm just going to go in order, guys. It's okay. It doesn't matter which cell you have. You're just designing it for one. Hans group, what do you guys want to do? I don't know your group, so Hans group is doing copper 2 sulfate. Whoever group that is. I know. No, I'll pop you guys. Or actually, you guys will. I'll pull somebody out of another group to you guys because you'll be 3 together. Chelsea, who's in your group? Or tell me what group. Okay, Han. Hydrochloric. Chelsea's. Okay. Nathaniel, what's back to you? Kevin.
silver nitrate.
Kevin is silver nitrate. And Alan, who's in your group? Gianna? Potassium sulfate. That's Maggie and Gianna. Okay. Whoever else. Okay. Strong. Different groups. Kevin's group. Shannon. Nitric acid. Have I gotten everybody? Hey, have I got everybody? Yeah. So Alex, substitute group last, and you might move into Nathaniel, Jack, and Alex here. Okay. So you guys are gonna get potassium iodide. I think that's the last one.
Yes.
Yeah. Okay. So KI for Nathaniel, Jack, and Alex. Oh, yeah. You guys are just making like maybe a 5-step process. It's not much at all. You're setting up an electrolytic cell, okay? That's it. Probably. Let me pause this video real fast.